Texan Global School. Normal form. In this class, the normal form of the equation of a straight line is analyzed, starting from a segment O, P1 of length P, and with one of its ends at the origin O. We can see that a positive theta angle, less than 360 degrees, is formed, generated by the radius vector O, P1. And by definition, its slope is defined as m1 equal to the tangent of theta. If we now draw a line L, which passes over the point P and is perpendicular to O, P1, as shown on the blackboard, we will obtain the equation of the line L, given the point P1 with coordinates x1, y1, and its slope m, using the form of the equation of a line given a point and its slope seen in previous classes. As a right triangle is formed by trigonometry, let us determine the values of the point. The abscissa is x1 equal to p times the cosine of theta, and the ordinate y1 equal with p by the sine of theta. So, to obtain the slope of the line L, we will use the condition of perpendicularity between L and O, P1. Let us remember that this condition says that m1 times m2 equals -1. When substituting the slope O, P1, obtained as m1 equal with tangent of theta, we have that the tangent of theta times m2 is equal to -1. By solving, we obtain the slope of the line L, defined as m2 equal to -1 over the tangent of theta. Remembering trigonometric identities, 1 over the tangent is equal to the cotangent of theta, and the cotangent of theta is cosine over sine. To obtain the equation of the straight line L, since we already have a point P1 of coordinates, p times the cosine of theta, p times the sine of theta, and the slope of the line L is minus cosine of theta over sine of theta, we substitute in the point-slope equation seen in previous classes. As we develop, simplify using trigonometric identities, since the sine squared of theta plus cosine squared of theta is equal to 1. Then we obtain the normal form of the equation of a line as x times cosine of theta plus y times sine of theta minus p equal to 0. In summary, the normal form of the equation of a straight line is x times cosine of theta plus y times sine of theta minus p equal to 0, where p is a positive number, numerically equal to the length of the normal drawn from the origin to the line, and theta is the positive angle less than 360 degrees, measured from the positive part of the x-axis to the normal. Let's look at an example. We will find the equation of a line in its normal form, if theta is equal to 60 degrees and p is equal to 1. In this case, substitute values directly into the normal form. Using exact values of the trigonometric functions, remember that for 60 degrees, the point to create the triangle is 1, the square root of 3. Therefore, the sine of 60 degrees is equal to the square root of 3 over 2, and the cosine of 60 degrees is equal to 1/2. Substituting values results x times 1/2 plus y times the square root of 3 over 2 minus 1 equals 0. Therefore, results the equation of the line in its normal form as x over 2 plus y times the square root of 3 over 2 minus 1 equals 0. We will graph to see the behavior of this line. Let's remember that to graph a line, we require at least 2 points. One way to get the 2 points is to substitute x equals 0 and y equals 0 separately. So, if x equals 0, by substituting and expanding we obtain that y equals 2 over the square root of 3. The first point is 0, 2 over the square root of 3. Now, if y is equal to 0, by substituting and expanding we get that x is equal to 2. Therefore, the second point is 2, 0. With these 2 points, we can see the behavior of the line. The distance p from the origin to the line is 1, and its angle is 60 degrees. We can also reduce the general form to the normal form of the equation of a straight line. Let us remember then that the general form of the equation of a line is ax plus by plus c equals 0, and the normal form of the equation of a derived line is x times cosine of theta plus y times sine of theta minus p equal to 0. So, to to reduce the general form of the equation of a line to the normal form, we consider both equations as coinciding lines. Therefore, their corresponding coefficients must be proportional. Then, as we saw in previous classes, when the lines coincide, we have that the cosine of theta is equal to k times a. The sine of theta is the same with k by b, and minus p is equal to k times c. Squaring equations 1 and 2 and adding them results sine squared of theta plus cosine squared of theta equals k squared by a squared plus k squared by b squared. Using trigonometric identities, remember that sine squared plus cosine squared is 1. If we now factor k squared and solve for k, we obtain that k is equal to 1 over, plus minus, the square root of a squared plus b squared. Substituting the value of k in 1, 2, and 3, we obtain the following relations, which, when substituted into the normal form of the equation of a line, we obtain the equation in the normal form of a line defined by the general form. So, in summary, what we must do to reduce the general form to the normal form of the equation of a straight line is divide each term of the general form by r, where r is equal to plus minus the square root of a squared plus b squared, considering that the sign of the radical depends on the following cases. If c is different from 0, r will have the opposite sign. If c is equal to 0 and b is different from 0, then r and b will have the same sign. And finally, if c and b are equal to 0, then r and a will have the same sign. In this other example, given the equation L of a line x minus 2, y plus 1 equals 0, we will reduce that equation to its normal form and find the values of p and theta from the general form given as a x plus b y plus c equals 0. We can determine the values of the coefficients. Then, a is equal to 1, b is equal to negative 2, and c is equal to 1. Now, we substitute the values of a and b to obtain r in the derived formula. We have that r is equal to plus minus the square root of 5. According to the theorem, since c is different from 0, r has the opposite sign. Therefore, since c is a positive 1, r will be negative. Then, r is equal to minus the square root of 5. Dividing the given equation by r and developing results the normal form of the equation of the given straight line. To obtain the values of p and theta, compare the coefficients of the equation obtained with the normal form. We can see that the cosine of theta is equal to negative 1 over the square root of 5. The sine of theta is 2 over the square root of 5, and p is 1 over the square root of 5. Remembering the class of the signs of trigonometric functions, we can see that since the cosine is negative and the sine is positive, the angle theta will be in quadrant 2. That is, it will be greater than 90 and less than 180 degrees. Then select the trigonometric function in which its ratio is negative, in this case the cosine, to obtain the angle in normal position. Solving for theta, we obtain an angle of 116.56 degrees. To graph, solve for y from any of the equations of the line, in this case in the general way, and we tabulate. We can then see the behavior of the line. The distance from the origin to the line, perpendicularly, is p equal to 1 over the square root of 5, and the angle in the normal position to that radius vector is 116.56 degrees. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com